Okay. So first of all, the lecture hour. The lecture starts at 8:40. Well, that is, I would prefer to start at 8:40, but if you cannot make it to 8:40, we can shift it to 9:40. Do you want to shift the course hour by 1 hour?
It's better.
Okay, so we will start at 9:40. At 9:40, the door closes. So if you are come at 9:41, too bad for you. You will miss the first hour. Okay. Now, this week we will be mainly looking at certain applications of the electrostatics. Well, the applications that we will be doing will, in fact, they are targeted at the future applications that we will be seeing. One problem we discussed was, for example, the surface charge. So how does the electric field change across the surface charge? That is one thing we had discussed. And in fact, this will be relevant when you, for example, take a material, put it in an electric field. So what happens is that the charges in the material will be shifted. The positive charges will be shifted in the direction of the electric field, negative charges will be shifted in the opposite direction, but that kind of creates a surface charge on the surface of the material. So effectively we can describe our system as a surface charge. Another problem that you had studied in your pre-report was the problem of the atom. Well, everything is kind of made up of an atom. You had made some models. You started with the model for a nucleus, what is the potential and the electric field of a nucleus. And in the book, there is a very simple model of the nucleus. It's basically a homogeneous charge distribution, a spherical homogeneous charge distribution. Well, the nuclei, are they spherical? Well, some of them are. Not all of them, but some of them are, especially you are studying quantum mechanics, right? Have you studied angular momentum? Not yet. Well, if the nuclei are not rotating, they will be mainly spherical. If there's a rotation, that is, if the nuclei has an angular momentum, and some nuclei do have an angular momentum, what you would classically expect is that they will look like Earth, compressed from the poles and a bit enlarged at the equator. In that case, of course, there is a breakdown of the symmetrical description, but nevertheless, the symmetrical nuclei is a good enough description. And what we, in general, in physics do is you start with a model, making simple assumptions, and then compare it with the observations. And if the model works, great. If the model doesn't work, you try to understand why doesn't it work, what is the assumption that doesn't work, what is the prediction that doesn't work, and try to fix it. And this way you increase your knowledge about physical processes. Now, the second problem you studied was the atom. If you consider the atom, the nuclei is very small. So it's almost a point-like object. Not exactly a point object, but at the scale of the atom, it just looks like a point. So you can describe it as a point. And then you have this point. Well, you had already seen quantum physics. Quantum physics tells us that the electrons, quantum mechanics in fact tells us that the electrons are not really points orbiting the nuclei, but rather they are described by wave functions, and hence they form a cloud around it. So we have this cloud around the nuclei. This is a very simple model of the atom. And then, of course, we can talk about the charge distribution. And again, it depends on whether the cloud of the electrons, is it symmetrical or not? But in the simplest case, it will be symmetrical. If it is symmetrical, then there won't be any angular dependence of the charge of the electron of this cloud. So the charge distribution will in fact be a function of the radial distance only. But if the charge distribution is a function of the radial distance only, everything is rotational and symmetric, this basically implies that the potential is radially symmetric. So this is the simplest model that you can think of. And in your book, there is a concrete model. Now, of course, we will be putting eventually these atoms in an electric field. And in fact, even in materials, every atom is in the electric field created by other atoms in the near vicinity. So if you put if you would consider, let's say, the radial distribution of charge. So we basically have a positive, this is the positive charges at the origin. And then we have kind of a cloud around the origin. These are the negative charges. And then you can calculate the, once you learn quantum mechanics, once you learn how to calculate the distribution of the electron in an atom, you can actually calculate the corresponding charge density. And once you have the charge density, you can calculate the potential. And then when you put this in an electric field, what will happen is the electric field will exert forces on these charges. The positive charge will feel a force in the direction of the electric field, and the negative charge will feel a force in the opposite direction. So if you just put this in an electric field, well, the positive charges will move slightly from the origin, and the negative charges will move slightly from the origin. Well, before its center was at the origin, for most atoms, at least for symmetrical atoms, the center of the negative charges is also at the center of the atom. So the object is neutral, it doesn't have any dipole moment, etc. It has, as we will see later on, it has higher moments. But if we put it in an electric field, the negative charges and the positive charges will be shifted. So you see the negative charge, the center of the negative charge is over here, the center of the positive charge is over here. So that is what we call a single dipole. And if you take any material, you can treat it as sheets of atoms forming the whole object. When you put this object in an electric field, well, each atom will be shifted like this. Each atom will be converted into a dipole. Once all the atoms are converted into a dipole, well, it just behaves like a dipole sheet, a very thin dipole. Of course, if you look at the charge distribution of this sheet, it won't be infinitely thin, but what will happen is you will have a region which is one side will be dominantly negatively charged, the other side will be positively charged. So this is basically how the charge distribution will look like in real life. But effectively, let's say this is the distance d. If there are some other time scale in your problem, like you will have, for example, you will be shining light, let's say. The light has some wavelength. If the wavelength of the light is much larger than d, or any other scale in your problem is much larger than this d, you can just approximate this d to be 0. You can just set that d to be 0. You have an infinitely thin dipole layer. So to study the materials, eventually we will also need these dipole layers. How does the dipole layer behave? So these are basically the physical reasons why we are studying these examples in this chapter. So eventually we will use them. And well, of course, there are the new techniques that you will be applying, new mathematical concepts that you will be using quite often throughout this semester, like the solid angle, etc. So these are also some practices. Now, one problem about the prayer reports, let's say one warning about your prayer reports, you see, the book, if you had read through the book, it is mainly based on examples. Now, next week we will, maybe even this week, we will start the next chapter. We had already started, it's the Green's theorem. But you see, if you look at the chapter, it is, besides what we had already discussed in the classroom, it is only examples. Because the book kind of teaches the material in examples. So, for example, in none of your prayer reports there is any mention of the capacitance. But in the book, the capacitance is both defined and studied in examples. So don't skip the examples. So for this book, at least, the examples are an integral part of the material covered in the book. Okay, so this is basically the overall summary of what we will be discussing. Now it's your turn. Questions? Yes.
There was one example in the book, and they were trying to calculate the potential in the nucleus system. And when they got to R equals 0, there was some problem with continuity. And I did not really understand how they resolved it.
The continuity, I mean the atom or the electric charge of the atom or the electric... The potential of the atom or the...
The atom, yes.
Of the atom. Answers. Did you understand the question? Do you know what's the example? You will be answering first of all, not me. So if you didn't answer and understand what he's talking about, you should ask him.
Defines the addition term. Addition term defines 1 over discontinuity using the function. That's not the term.
So what were they talking about? I think this was the potential, right? No, beta is a function of alpha. Was it equal to alpha? Okay. Is that? Well, I mean, I don't remember the exact coefficient. It was some other constant, but of course that constant is related somehow with alpha. Because we know that the total charge creating this electrostatic potential should be 0. So that is how we can fix beta in terms of alpha. So what was the question? What was the answer? So first of all, let's change our seating plan. I mean, when you sit on the back, nobody is listening to you. You move to the front seat, Giray. Here, you move here. You also come to... And when you two talk to each other, we don't hear you. You should be speaking to everybody. Seni de biraz öne alalım Anıl. Seni de Anıl'ın yerine alalım. Seni. So that everybody can see everybody else without turning around. Starting from next week, Rıza, we will be doing the lecture at 9:40, not 8:40. At 8:40, nobody shows up. Okay. No, it's not really important for the question, neither for the answer. Yes? Now, he's talking about this potential, right? So he was... Answer?
Before we have the charge density function, then we can integrate over the whole space, we get the result. But it explains also the charge at the 0 point. The additional terms come from here. Solves the discontinuity of the potential function.
So where is the discontinuity? This is the continuous function.
At RQ 0 points.
Well, that's a divergent point. It's not a discontinuous point. It diverges there. Well, the problem is this is not defined for r less than 0.
This potential for the electron,
Yes.
It says because of the nuclei screened by inner electrons, we should use Coulomb potential like this. I really don't understand why this one.
Why this one?
Why this one? How we define this one?
Well, the exact calculation of this potential, as I said, you need quantum mechanics. Without quantum mechanics, we cannot really solve this problem. But we basically know what to expect. So there is a positive charge density at the origin, which corresponds to the nucleus. This is very small. And then the electron is spread out, so that the total charge should be 0. But, for example, this is our model. Does this potential give us a model corresponding to, well, a charge density corresponding to our model? Now, how do you calculate the charge density starting from the electrostatic potential? You apply the Laplace operator. This should be equal to minus 4 pi rho. Now, the problem is at r is equal to 0, our function diverges. So you cannot really talk about the derivatives of this function at r equal to 0. So we have to do something else. Now, what the book does is it just separates this into a part that is finite at origin and a part that is divergent at the origin. So he says that this is equal to e to power minus alpha r minus 1 over r. When you put r is equal to 0, this is finite. If you just take r equal to 0 limit, this is just 0 over 0. If you take the limit properly, this just gives you minus alpha. Of course, there is the minus alpha, e to power minus alpha r over r, but now we have to add the 1 over r. So there is this separation. So the first two terms, no, not the first, there's no r over here. The first two terms are finite at r is equal to 0. So we can talk about their derivatives even when r is equal to 0. It is the last term that is not finite at r is equal to 0, but we already know that the Laplacian of 1 over r is nothing but minus 4 pi times Dirac delta. So for the first two terms, this is equal to 1 over r squared d by dr, r squared d phi by dr. Since phi is a function of r only. So the theta and phi derivatives do not appear in the Laplacian. So what is the charge density? Yeah, at least we see that there is a Dirac delta appearing over here. So that would give us the charge density of the nuclei. In this simple model, it is approximated to be a point charge, so the density is a Dirac delta, plus some other smooth function, which will correspond to the charge density of the electron cloud. Yes, so this half of the classroom already asked the other half of the classroom your questions or comments on this question.
I have a question.
Okay, first it's their turn. They are too silent. Homogeneous, let's see. Let's calculate the charge density. Okay, so this was our phi. Let's first evaluate it. R is not equal to 0. Okay, d phi by dr. We already know its expression, so this is equal to minus alpha, the derivative of the exponent first, plus or minus 8 power minus alpha r over r squared plus 8 power minus alpha r over r times minus alpha. So this is the first derivative. Let's multiply it with r squared. This is equal to, let's say, all of them have the factor e to the power minus alpha r over r minus alpha plus alpha squared r minus 1 over r plus alpha minus alpha. Multiplied by r squared. So we have some cancellations. So this r also cancels. This r, let's take its derivative. Okay, so this will be minus alpha times e to the power minus alpha r minus alpha plus alpha squared r minus 1 over r times r. This is the derivative of the exponent. Plus e to the power minus alpha r times minus alpha plus alpha squared r minus 1 over r. This is the derivative of the r term. Plus the derivative of the bracket. So alpha squared plus 1 over r squared. So rho is equal to minus 1 over 4 pi times 1 over r squared d by dr, r squared d phi by dr. We already had calculated this derivative, just divide it by r squared, and that would give us minus 1 over 4 pi r, 4 pi, e to the power minus alpha r, and divided by r squared. These are common. What remains is alpha squared r plus alpha cubed r squared minus and plus alpha minus alpha plus alpha squared r minus 1 over r plus alpha squared r plus 1 over r. Okay, if I didn't make any mistakes, these cancel. Alpha squared r's, there are 3 of them. Okay, 1, 2, 3, and yes. Or let's say 1 over 4 pi e to the power minus alpha r divided by r cubed, 3 alpha r squared minus alpha r cubed. Of course, this is for the electron negative charges only. because the positive charges we had separated. The positive charges this one gives the positive charge, basically. It is the 1 over Dirac delta R, it's the charge at the origin. Of course, this is one way of calculating the charge density. Another method that you could have used is just assume a sphere, then E dot ds on the sphere is just 4 pi times Q enclosed. But on a sphere, the electric field, you see, the electric field is basically the derivative of the potential with respect to R. Because the potential is spherically symmetric, only the radial derivative exists. The theta and phi components of the electric field does not exist. So this integral will be E at the position R, which is a constant which I can take out of the integral, times, of course there's only the radial component, times 4 pi R squared. Well, E at the radial distance R is nothing but minus d phi by dr multiplied by 4 pi R squared. So the enclosed charge is equal to minus R squared d phi by dr. This is the charge in a sphere of volume R. Now let's see, we had already evaluated that derivative. Now what I would like to do is take the limit R goes to 0. What is the enclosed charge? So I take an infinitesimal sphere, and if the charge doesn't contain any Dirac deltas, the charge should go to 0. So this is my phi. I multiply it with R squared. Let's look at the first term. The first term, when multiplied with R squared, it just becomes R times 1 minus alpha R proportional to, let's say. And when I set R is equal to 0, that just goes to 0. When I look at the last term, this is just proportional to R. When I multiply it with R squared, again, it goes to 0. And the only term that survives is this term over here. When I multiply with R squared, it cancels this 1 over R squared over here. Well, this alpha R term goes to 0, exponent becomes just 1, so I have minus 1. Minus 1, there's a minus over here, plus 1. So a sphere that has infinitesimal radius nevertheless has a total charge of 1, plus 1. Well, that is what we call the positive nuclear charge. So definitely this potential corresponds to a point-like charge at R equal to 0. The remaining is the electron cloud, and it definitely is not uniform. It decays exponentially even at larger separations. And we would have expected that exponential decay even from this simple picture. Well, it could have been e to the power minus alpha r, an alternative model could be e to the power minus alpha r squared, etc. But they don't really make too much of a difference. The critical thing in our model is we have a Dirac delta at the center, plus a negative charge distribution that decays at infinity. Have you studied the atomic levels? At least in your chemistry courses, they should have mentioned it, the courses that you missed. Maybe. For example, if you go to higher and higher orbitals, you will see that it's not just a single bump, there are more bumps.
This major chemical engineering.
Well, you probably didn't miss those courses. Well, you see, if you have the excited states, this is the ground state. The excited state, well, you expect it to have a larger energy. If it has a larger energy, so it will be probably moving away from the nuclei, not at the nuclei. So it's likely to have such a shape. Now let's say as a function of r. And then if this is the n equal to 0, this is n is equal to 1. Well, let me erase the r smaller than 0 part. By definition, r is larger than 0. And then if you go to higher and higher energy levels, the charge density will have more bumps. This is what we would expect. And once you study it in quantum mechanics courses, you can just look for it. So they have this bumpy structure as you go to higher and higher excited and excited states. You will be solving the hydrogen atom this year. Any comments, questions on this one? Yes, other questions?
No, maybe I get it more around later. As I remember, it says that there is also a positive space charge.
Well, let's see. Now, there is a positive space charge at the origin due to the nuclei. It's a point. And out of the nuclei, I don't expect any positive charges. Well, let's see, what is the expression for the charge? Here we have this function over here. So what does this function look like? First of all, let me ask you, there is a minus sign over here, so it looks as if it is a negative charge. Assuming that if this is always positive, then there is a negative charge. Is that always positive? What does it look like, that function? That part only. So let's say as a function of x, 3x squared minus x cubed. Of course, there's plus the exponential, etc., but the exponential doesn't change the sign. Yeah, you see, for x small, x cubed is very small, much smaller than x squared. So for very small values of x, this will be the term that will determine its shape, its sign, its behavior. And that is a parabola. Now, of course, when x is equal to 3, it becomes 0. Let's say x is equal to 3 is over here. What is actually happening is as x gets, for very small x, the dominant term is 3x squared, but as x gets larger and larger, the x cubed term starts to be more dominant. And when x is equal to 3, they have the same sign. And after x is equal to 3, the x cubed term will be dominant. So this is the shape of this term over here. And as you see, yeah, there is a region where the charge is effectively positive, the charge density. Now, I would have preferred a model in which the charge density is always negative except at the origin. So basically, I mean, this part is not necessarily only the negative charge. So the nuclei is also somehow spread over the atom in this model.
Also, we have no gap. Also, we have no gaps.
In the charge distribution, there's no gaps. Well, there is one gap in this model. When R is equal to 3 over alpha, there is a gap. When alpha R is equal to 3, the charge density is 0. But it's just a sphere. So in this model, basically, you have a nuclei. Around it, there is a spherical region which has a negative charge. And out of this spherical region, there's some positive charge. Of course, in this positive charge, due to that exponential, the positive charge is very, very small due to that exponent. So there's an e to power minus alpha. E to power minus 3 is something like 20. 1 over 20. Of course, this is assuming that I didn't make any mistake in the computation here.
Can we express charge distribution in terms of wave function?
Sure. You will do that in quantum mechanics. You see, the electron charge density will be nothing but this one. Psi r squared is the electron probability density multiplied by the charge of the electron minus E. That gives you the charge density corresponding to the electron. So if you want to obtain the electronic charge density, you should obtain the wave function.
Layers of dipole, we have the potential difference, but the looks defined as a potential loss between layers. Why is defined as loss?
A change. I mean, you see.
What's the number? Why not gain?
It's just convention. I mean, you can go from, let's say, the negative layer to the positive layer and say that the potential loss is negative, or potential gain is positive. The change. Just keep in mind that it was written by a German.
For the dipole, so if we take the Gauss around the dipole,
Okay.
shouldn't we get the field equal to 0?
Not the field equal to 0. Yes, answers. I'm not the one answering all the time. You should stop me. So his question is, if you take the Gauss surface around the dipole, the total charge of the dipole is 0, so the electric field should be 0, no? Why not?
Factorial and area factorial. Summation is 0, not electric.
Does it convince you?
So think about that. Doesn't have the atom dipole moment? Or electric field?
Yes, it does.
It's motion. static organisms.
We have the electric field in different directions when you do some they cancel each other.
So this is basically the shape. So if you assume a Gauss surface, let's say like this, containing both of the charges, the net charge inside is 0. So the integral of E dot ds is 0. But you see here, this is the direction of the electric field. ds is also more or less in that direction. So E dot ds, is it larger than or equal, less than 0? Larger than 0. If you look at this region over here, this is the electric field, and this is ds. E dot ds, less than 0. So basically, when you are taking the integral over the surface, you have regions where E dot ds is positive and other regions where E dot ds is negative. So the sum turns out to be 0, although the electric field is not 0.
So the flux is 0.
The flux is 0. Now, of course, if you would imagine such a surface, in that case, E dot ds is not 0. But in the book, we are assuming the dipoles are almost point-like. We are taking the limit of point-like dipoles, so there's no sense in talking about the surface passing through the dipole.
Potential of the dipole there, we have a term including solid angle. For example, if you have an infinite dipole there, the comp somewhere.
Well, let's see.
Under it, how can we calculate?
So this was the expression for the potential change. Right? Correct. Yeah. Hmm? What is square? No, that was cube. And so your question? So why, if we take an infinite dipole layer,
Something like this. Not straight, somewhere.
we can also have a straight. There was one of you asking this question, I suppose. So if I'm not wrong. Well, this is a capacitor, before discussing your question. This is a capacitor, so this is positively charged, this is negatively charged. So can we use the dipole approximation? Can't we treat this as a dipole? D omega is our solid angle. So can we or can't we? What will be the potential in this case? Is that at this point?
capacitor equals zero.
Well, let's see. The dipole density is constant. So phi is proportional to the dipole density, which is constant, d omega. D omega is 2 pi. Now, it is definitely not zero. Oops, how come? As your friend said, we said that outside the capacitor it was zero. Or did we say that?
Electric field is zero.
Electric field is zero. So if an electric field is zero in a certain region, what can you say about the potential? Constant. That's what we find. You see, this 2 pi doesn't depend on which point we are. So it's just a constant. So there's no problem. The potential is non-zero. And plus the potential has to be continuous. And of course, in general, we set the potential at infinity to be zero. But for an infinite layer, we cannot even do that. What we know is the potential difference. Well, the electric field inside, we had calculated its magnitude to be sigma over, let's say, 4 pi sigma. 4 pi sigma. So the potential difference is equal to 4 pi sigma times d. Well, sigma times d is what we call the dipole density. So this is the potential difference between this point and that point. So the lower half plane has has a constant potential. Our upper half plane has a constant potential, and hence the potential cannot go to zero at infinity. So the potential at infinity, we can set it to zero only if we have a localized charge distribution. If the charge distribution is somewhere over here, in that case we can say that the potential at infinity is zero. This is an example where we have the charge density is not localized, so we cannot set the potential at infinity to zero. Another example was an infinite wire. In that case also we cannot set the potential at infinity to zero. Now back to your question. You are saying that we have some dipole density Okay, what was the question? What did you understand? Share it with your friends.
My problem was how he calculates via subcomponent.
Mm-hmm. So what is the solid angle? What's an angle? So what is theta? Okay. Okay. So angles, we define it in 2 dimensions. And in 2 dimensions is the distance of the arc divided by the radius of the circle. So that's basically how we define an angle. Now, of course, we can generalize this. I mean, just take any shaped object. So, and this is L, this is theta, this is, well, let's assume a very small one. So this is dl, this is r. And then you can just say that d theta will be dl, let's say cosine of some angle, divided by r. Well, basically, it's not the dl. We have to imagine kind of an arc of this shape. What we are interested in is that shape over there, the length of that arc. And the length of that arc, if we define this angle to be, let's say, phi, not theta, the length of that arc is nothing but this length divided by cosine phi. So that is why we have the dl cosine phi over r. Well, of course, the reason why I defined it as dl is that the distance of every point on that segment is different. But if we take a very, very small segment, that very, very small segment, the change in r will be negligible. So for that very small angle, we can still talk about the distance of that arc from the origin. This is still how we can define d theta. Now, well, this is at least a neater definition, which you can generalize to arbitrary curves. Well, the generalization of a circle in 3 dimensions is a sphere. Imagine a sphere. Well, the generalization of an arc in 3 dimensions is just some surface. It can be an arbitrary surface, not necessarily a smooth one. Let's say this is the area A, and then you can just imagine a cone. Instead of, you see, here we had this wedge-like shape. If we generalize it to 3 dimensions, what we will get a cone with the bottom area equal to our area. This is the cone. Well, the radius is r. The solid angle we define as a. Well, you see, before L had the dimensions of radius. So if the radius was larger, L becomes larger linearly with the radius. So that's why we define by r. So this L over r is in fact independent of the radius. It only depends on the angle over there. If you imagine a larger circle, a circle that is twice as large, r will become twice as large, but L will also become twice as large. So if you take the ratio only depends on that angle over there. It doesn't depend on the size of the circle you imagine. Well, in the case of a sphere, the areas, they increase with radius squared, not with the radius. So if you want to define a concept that is independent of the radius of the sphere, you have to divide by r squared. And this is actually what we call the solid angle, area over r squared. Now, in this example over here, I straight away wrote that the solid angle was 2 pi. Because I can just imagine, instead of this plane, I can imagine this hemisphere. For every area over here, there is a corresponding A prime on the sphere. And you see, and the definition of the solid angle or any angle actually depends on this region, that wedge, the tip of the cone, let's say. It doesn't depend on whether I take the area A to define it or I take the area A prime to define it. Since we are dividing by radius squared, well, if I take the larger, this area, the area is larger, the distance from the origin is larger. So the ratio is the same as if I take this area over here. The area is smaller, but the radius is also smaller. And so whatever area I imagine on those infinite plates, they have a corresponding area on the lower hemisphere. So the area of the lower hemisphere is the total area. The total area of the lower hemisphere is 2 pi r squared. Divide by r squared. The solid angle corresponding to an infinite plane is always 2 pi, no matter where you are. Well, if you are at the lower plate, that becomes a minus 2 pi. So the difference is 4 pi. The difference in the potential between the upper region and the lower region.
You can't use this formula for finite surfaces.
Let's take for a sphere, right? Well, let's see if we can use it for a sphere. Let's say we have a charged sphere. The total charge Q, radius R. Out of the sphere, let's see, it's a, well, we can imagine it as a dipole layer, right? Well, we can solve this analytically. First, let's try to solve it analytically, and what is the potential outside. Phi r, right, will only depend on r. We are outside, let's say at this point. This will be equal to the charge of the positive shell divided by r plus, no, not r plus, in fact, just r. Do you agree? Plus the charge of the negative shell divided by r. So this is equal to q plus q minus divided by r. And this will be about 0, right? Let's see if our expression gives us the same result. We are looking at the potential over here, and we said that the phi is equal to dr prime d omega. Let's look at what d omega is. This is basically our d omega, or omega. Well, let's see, we can, of course, the derivation is based on a single sheet. So here we can just divide it into 2 sheets. We are on the positive side of one sheet and the negative side of the other sheet. And both sheets cover exactly the same solid angle. So it will be the contribution, let's say, from the nearby sheet times the solid angle, plus the contribution from the further away sheet times the solid angle. This is equal to 0. So it's a finite dipole layer and the total potential is 0. So we can use it for finite sheets also.
How do you know it's constant density?
The constant density, well, let's calculate the density. Let's first start with this example. We have finite distance. There is a sigma plus, there is a sigma minus. This is at distance r1, this is at distance r2. Sigma plus and sigma minus, they are not equal to each other, because at least in the first example over here, I assume that the total charge is 0. So that I still would like to study the same case. The dipole layer should have a total charge equal to 0. But if the total charge is 0, sigma plus and sigma minus, they are related to each other. Sigma plus times, well, let's say r plus r minus, r plus squared, should be equal to sigma minus times r minus squared. Now, what is the dipole moment? If you remember, the definition of a dipole moment was equal to... yeah, okay, so this is not nice because in the definition of the dipole moment, the densities are the same. So I would rather stick with common densities. But then we have to modify the previous solution a bit. Well, this was sigma times d. Yeah, this is constant. So the dipole moment density is constant. Because if we assume that the sphere is homogeneous. And only if we assume that the sphere is homogeneous, we can use these expressions, because for a homogeneous sphere, spherical shell, the system, if we are outside this shell, the system behaves as if it is just a point charge at the center. So at this here, when we are setting that phi of r is equal to 0, that is q plus plus q minus is equal to, phi plus is equal to 0, because we are assuming the charge density has a spherical symmetry. Now, of course, there is another issue if we assume that sigma is the same, q plus and q minus, they are not the same. Q plus is sigma times r plus squared, and q minus is sigma times r minus squared. What we are looking for is q plus plus q minus. Is it 0 or not? This is equal to, now q minus is minus sigma times r minus squared. This is sigma times r plus squared minus r minus squared. Well, let me also add the 4 pi's. This is equal to sigma times r plus minus r minus times 4 pi times r plus plus r minus. When we are taking the limit that r plus and r minus, they go to 0, we are assuming that sigma times, well, this is the r plus minus r minus, this is d, this is our d, which we assume to be constant, times 4 pi r. Well, let's see. If q plus plus q minus is 4 pi r times d, then the potential outside, this was q plus plus q minus divided by r. This is equal to 4 pi r times d over r. What's wrong? Well, here I claim that d plus and d minus, they have the same densities, and the solid angle is the same, so phi should have been 0. Well, you see, this is the expression, the general expression obtained. And from this general expression, I said that, okay, so the D is constant. Since it's constant, I can just take it out of the integral. I have two sheets, one this sheet, the sheet that is closer to omega, and then the other sheet, the sheet further away from omega. So it is the sheet closer, I called it the dipole density as D plus omega. Well, why did I call it D plus? Because we are on the side of the positive side of the dipole. The dipole is pointing towards us. And the other sheet, the piece of this sphere that is away from us, I called it D minus because the surface that is looking at us is the negative sheet, negative side. And both of them cover the same solid angle, this solid angle basically. And D plus and D minus, they are the dipole densities. They have the same magnitude. So they cancel. But then, as you said, they don't necessarily have the same charge. So this, by just looking at the total charge of the positive shell and the negative shell, we said that phi at the position of R should have this expression, Q plus plus Q minus over R. So we should first calculate what is Q plus plus Q minus. Well, Q plus is sigma times R plus squared, and Q minus was minus sigma times R minus squared times the 4 pi. And then what we said, okay, let me just sum them up. I have this expression over there. If I just put R plus, if I just set R plus and R minus equal to each other, in that case, definitely this expression goes to 0. But you see, when we are looking at the dipole layers, we do two things. We first set the separation go to 0, but at the same time, the charge density goes to infinity, such that sigma times D is finite. Well, I can factor this thing out. Then I have the sigma times D multiplied by a finite number in the limit of infinite thin sheet. And then Q plus plus Q minus is 4 pi R over D. And so our expression for the potential is non-zero. So at least in one of the derivations, in some place we are making a mistake. What is our mistake?
So the distance between the two sheets is 0, then 1 plus minus and 1 should be 0.
Exactly. But you see, we are taking two limits together. One limit, we are setting R minus equal to, let's say R minus to equal to R plus, that is one limit. But at the same time, we are taking the sigma goes to infinite limit in such a way that sigma times R plus minus R minus is finite. No, the product, D goes to 0. That's the limit we are taking. But at the same time, sigma also goes to infinity in such a way that their product is finite. D capital. Yeah, D capital is finite, yes. Yes. And this is the limit we are taking. D goes to 0, sigma goes to infinity such that sigma times d goes to capital D. No, R minus is not going to 0. R plus and R minus, they are going to R. R is this point. We are looking at the potential, let's say, at this point. This is our R. Sorry? True.
D should include both sheets, right?
No, D, you see, D is defined locally. If you look at a point on the sheet, there's a D. If you look at another point, there's another D. At every point on the sheet, there is some D. Well, of course, there is a plus or a minus sign depending on whether you are close to the negative sheet or the positive sheet. So that's why I put that D plus and D minus. Yes. You see, not always, but here D is constant. Since D is constant, if you are on the positive side, you have the plus D. If you are on the negative side, you have the minus D. What is it that we are missing?
This is wrong.
Hmm?
This is wrong.
Which one? Is it wrong? I don't know. I mean, you see, let's see. We had various derivations. Here we said that, okay, we have a plus charge, minus charge divided by R. The charge density will not be uniform if the D is non-zero, but the total charge should be 0. And if the total charge is 0 on a sphere, then outside the potential should be 0. Then we use the expression in the book for a dipole layer, which also gives us 0. So at least here, everything seems to be perfect. But then, well, you see, if you assume that the smaller sphere and the outer sphere has the same charge, that means they have different charge densities. But the dipole is usually defined as two sheets with the same charge density. But if you have two sheets having the same charge density, that means the inner and the outer sheets will have different total charges. Well, if they have different total charges, of course, this difference will go to 0. That is hopefully. But you see, when we sum them up, and when we take the limit as their separation goes to 0, keeping this dipole density constant, then the total charge of my system turned out to be non-zero. And hence the potential outside is non-zero. So which one is correct, which one is right? Why is one wrong, the other one correct? What are the assumptions we made? Are they wrong? Don't they apply? Which treatment should we take? Upper one, why?
Times the
This one is correct, you mean this one?
no.
This one?
Yes.
Is that correct or wrong? Wrong, why? How should we correct?
We cannot define D because
Well, you see, I can take this limit, common charge density,
We have two charge densities. How can we calculate the total dipole density?
why not? You see how we define the dipole density in the book, how was the derivation. You take two sheets, very thin. Well, if you take a point, this is the point, let's say R prime. At this point, you have this area over here and another area over here. Let's say at this point, the charge density is plus sigma R prime, and here you have the minus sigma R prime. Well, of course, those 2 points are different points. In fact, you should be using this sigma not at R prime, but at a different point. But we will eventually take the limit of infinitely thin sheets. And when we take the limit of infinitely thin sheets, all those points will be the same point, R prime. So that's why I just denote them as R prime. And then we have this separation, D. And we define this, let's say, normal vector N from the minus sigma sheet to the plus sigma sheet perpendicular to the surface. And then we define D as limit as D goes to 0. Well, let's put the vector sign. D is sigma goes to infinity such that D times sigma goes to some constant, some number of D times sigma R prime in the normal direction. This is how we define the dipole density. So what are the assumptions we are making here? Well, we are taking that limit. In every case, we are taking that limit. Well, here it's not uniformly distributed. I mean, you see, sigma can have a different value at different points. What is the total charge of the system? 0. That's an assumption we are making. We are treating sheets of 0 total charge. No, they do have 0 total charge. Let's see. Let's go back to our example. You see this one. Well, this result, the potential we obtain in this derivation differed from what we would obtain from the result in the book. Because basically, in this derivation, the total charge of my system is non-zero. Since the total charge is non-zero, of course, the two results will disagree because they are not derived using the same assumptions. Here we have a total charge. And the potential is actually the potential created by the total charge. There is no additional potential due to the fact that we have a dipole layer. So this is the charge due to the total charge of my system, which we can model as a total charge at the center, plus the potential created by the dipole layer itself, any additional contribution. But that additional contribution is just 0, just like we obtained over here. Well, to be able to, in this derivation, we started by assuming that the total charge is 0. Well, of course, sigma plus and sigma minus, they have different values. Nevertheless, the difference goes to 0 when we take the sigma goes to 0, d goes to, sigma goes to infinity, d goes to 0 limit. And hence, this result still gives the correct answer. So essentially, all our 3 results, they are correct. They're not wrong. But just one of them is derived using a different assumption, which doesn't hold for the previous 2 cases. So that's why they look different, but nevertheless, they are all correct for different cases. Well, you see, the derivation in your book, based on this dipole layer picture, you see what he says is for every area element over here, there is a corresponding area element over here. And this has charge plus sigma, this has charge minus sigma. So you define a local dipole density at that point. But that dipole has total charge 0. So if we just sum all the dipoles, the total charge creating the given potential is still 0. So the result, this one over here, this result over here is derived based on the assumption that the total charge of your system is 0. If there are additional charges which do not form your dipole layer, in that case, you will, of course, add it to this one. Now, what does it correspond to? Let's say in this case over here, you see the dipole, this is not a dipole layer, in the sense that the outer area and the lower area, they are different. So what we should do is kind of just eliminate this area from here. No, sorry. So eliminate this area over here, and the inner area, they are equal. So for these areas, just imagine opening them up. Then you can imagine that they are, that's a dipole layer. But plus we have some additional charge. So when we calculate the total potential, we have to well, in this problem at least, when we calculate the total potential, we have to consider the charge of the dipole layer plus the charge of this potential, the potential created by this extra charge. Well, how much is that extra charge? Well, here this is just a sketch. I mean, don't take it this. I mean, that area is not really localized at a given point. So you just take very, very small strips of areas at every region. So still it forms some kind of a spherical distribution of additional charges. And those additional charges, they create this total charge of the dipole layer, which we have to add to the potential created by the dipole layer. So that is why in this case, we obtained a non-zero potential because the total charge of my system is non-zero. The areas, you see, the areas are same. The difference in the areas, that is, well, this additional charge will be equal to, let's say, sigma times delta A, which is 0. But you see, we are taking the limit. Delta A is actually sigma times 4 pi r plus squared minus r minus squared. We are taking the limit as r plus and r minus, they go to the same number. D goes to 0, but sigma goes to infinity. Now this is 8 pi d times r, not 4. Because r plus plus r minus becomes 2r. So this is the additional charge. You are right, the difference in the area goes to 0, but the charge density diverges at the same time, such that the chain difference in the area multiplied by the charge density is finite. So if we treat this as a dipole layer with the same charge density, it has a total net charge. Whereas this expression over here assumes that the net charge is 0. Hmm? Well, you see, all of them are correct. But what is your system?
Two are the same system, right?
Well, you see, do you have a very thin shell with a 0 total charge? Is that your system? In that case, well, the net charge is 0, so the potential outside will be 0. Well, you can treat that very thin shell as a dipole layer, and the dipole is 0. Or do you have a very thin shell, which is a dipole layer? You can say that it's a dipole layer, but it also has a total charge. In that case, that dipole layer doesn't really create any potential outside, but the total charge does. So what is your system? Do you have this spherical object that is neutral or charged? So that is your problem. I mean, you have to define your problem. Does it have a net charge? So you have to add the potential due to that net charge. Is it the net charge is 0? You don't add it. It's just a dipole, whatever the dipoles create. So in that sense, all of these three answers are correct. They are just referring to different systems. Well, the top two, this result and this result, they are referring to the same system. Whereas this one is a different system. This is a system. The difference between this system and the above system is that this system has a net charge. The above system has a 0 net charge.
Why doesn't this system go to the other system immediately?
Because, I mean,
Why does it not go to 0?
the problem is in the limit. When you are taking these limits, you see, the above system, what are the limits we are taking in this system? We are taking the limit that Q plus goes to Q minus, or let's say sigma plus goes to sigma minus. Goes to infinity. And also D goes to 0, such that sigma times D goes to D. In the below system, we are taking the limit Q plus goes to Q minus actually. So basically, we are taking different limits. In this one, we are taking the charges, different charges. They approach each other, and each one goes to 0. In here, we are taking the densities approaching each other. The charges are fixed. So they are basically different. Eventually, they correspond to almost the same thing, but they are different limits. In one of the limits, we obtain a system of neutral system. In the other limit, we have a system that has a total net charge. So since indeed the limits are different, we don't end up having the same system, and hence the potentials are different. Okay, so for today, let's end it here. Well, the one good thing about this system of lecturing is that students usually forget to take a break. I mean, if you ask for it, I will give a break. But almost never they ask. I mean, they just forget about it. And the good for me, the bad for you is you cannot just write a one-page pre-report and expect to come here and sit silently. Okay, so that is kind of, I mean, there's no way you can just do a very little work at home and come here. I will disturb you, your friends will disturb you. So you should come here already prepared, having something to discuss. And the Monday lecture, I will check for the classrooms. We will start at 9:40, not 8:40, so that you will come on time. And well, if there are no class, I will let you know. Any last minute questions? Yes.
Can we consider the motion of the electron as a wire
Mm-hmm.
carrying current? So there is a magnetic field. What's this effect?
Well, okay, first of all, the magnetic fields we will be discussing probably in a month, not yet. The current carrying wire, it depends on your system. I mean, if you are making very precise measurements, then you will be able to tell where the electron is. But if you are not making that precise measurements, well, the electron, you will not really see where it is, but you will see that it's just, at least in the Bohr approximation, let's say, it will be just making this fuzzy rotational motion, and which will create a magnetic field. Well, the problem is usually, I mean, for example, in quantum physics, you will be discussing it. So what does this magnetic field create? For example, the electron is rotating constantly. It has this, it creates this current, which creates a magnetic field. The nucleus is at the center, kind of sitting there, let's say, but it has a spin. The spin means it has a magnetic dipole moment. Well, you put a magnetic dipole moment in a magnetic field created by the electron. They will influence each other. So in the Hamiltonian, you have this additional contribution to the total energy. There is you put the magnetic dipole moment of the nucleon in the magnetic field created by the electron. That is what you call the spin-orbit coupling. But you will study these in more detail in quantum mechanics. And here, what other effects, if you put this spinning of the electron, well, it creates a magnetic field, as you said. But usually the magnetic fields of different electrons, they are just oriented randomly. So there is no net magnetic field created. But if you put this system in an external magnetic field, well, the external magnetic field will rotate the orbits. So it will change if you apply a magnetic field in a material, it will change the applied magnetic field, the total magnetic field. So that is when we discuss the magnetic field in matter. So first, electrostatics. Next week, we will continue with Green's function, mainly with the applications of method of images. That is the examples in chapter 2. And then we will be doing in electrostatics in matter. Other questions? Okay, so no recitation on Wednesday. No recitation this week. And then we will meet on Friday.